Hello, we start with a beaker of very cold ice, let's say a negative 20 degrees Celsius, and we supply heat to it, constant rate, and we measure the temperature at regular time intervals. So if you were to plot the temperature versus time graph, how do you think it will look like? Typically, it will look like this. So the temperature rises at a constant rate, and then it stays constant for a while before it climbs again, and then stays constant for a while, and then climbs. So why doesn't the temperature rise continuously? After a while, every student will say, it's because it's ice here and it's water, then it becomes water, then it becomes steam. So those portions when the temperature stays constant must be when the ice is melting and when the water is boiling. Wow, so clever, huh? But the question remains, because we are supplying heat continuously, the ice or the water is absorbing energy continuously, right? So why doesn't the temperature rise? Now remember, the internal energy consists of two parts, right? The microscopic Ke and the microscopic Pe. Now which component is related to the temperature? Only the microscopic Ke, right? It's the average microscopic Ke that's proportional to temperature. When we measure temperature, we are measuring how vigorously the atoms or molecules are vibrating or moving. So the other component, the microscopic Pe, has nothing to do with temperature because this component is related to the intermolecular bonds. So during melting, all the heat energy must have gone into increasing these components only. In order to melt, we must increase the microscopic Pe so that H2O molecules in the ice can break free from one another to become the H2O molecules in water. So all the heat supply goes into this, the microscopic Ke stays constant, and therefore the temperature is measured to be constant. And the same thing happens during boiling. So yay, puzzle solved, right? Not so fast, yeah? Let me test you. Say we have 1 kilogram of ice at 0 degrees Celsius, and we have 1 kilogram of water also at 0 degrees Celsius. Can you tell me who has more microscopic Ke and who has more microscopic Pe? Are you ready for the answer? Let's talk about the Ke first. Now, I said that both of them are at 0 degrees Celsius, right? That means the H2O molecules in the ice and the H2O molecules in the water are vibrating just as vigorously. Because if they are not vibrating just as vigorously, then they wouldn't be at the same temperature. So microscopic Ke-wise is the same for both of them. As for the microscopic Pe, it must be different because the microscopic Pe is about the intermolecular bonds, and you know that the H2O molecules in ice are much more strongly bound to one another compared to the H2O molecules in water. But who has higher microscopic Pe? This is the tricky one. Let's bring in steam as well. So let's compare ice, water, and steam. Who has the highest Pe? Now if you assume the steam to be ideal gas, then it has 0 microscopic Pe because there's no intermolecular bonds at all. The H2O molecules in steam are just zipping around like crazy, independent of one another. So total freedom here means 0 microscopic Pe, which means in water we have some negative microscopic Pe, and in ice we have even more negative microscopic Pe. So ice must have lower Pe compared to water, and water must have lower Pe compared to steam. It has to be like this, right? That's why you need to supply the latent heat of fusion in order to melt the ice. Where does the latent heat of fusion go? It goes into increasing your microscopic Pe so that it goes from very negative to not so negative. And similarly, you need to supply the latent heat of vaporization in order to boil the water. Where does this latent heat go to? It goes into increasing your Pe from some negative value to 0. It may be a bit counterintuitive at first, but the more bonded you are, the more negative your Pe. Because the more bonded you are, the more energy that's required in order to set you free, because to be free is to have 0 Pe. Alright, that's all. Ta-ta!